let me move this picture, okay, so that I can start explaining the rest of the problem. So for the designing for the calculation of moments, okay, so in our case, in this example, our footing is same in this long direction and short direction, 3.3 meter by 3.3 meter. So for calculating the moment, so we have to calculate the length at this edge of this footing, okay, cantilever length in short direction, so you can say this direction B. So the our lengths are same, so I will calculate in long direction. So because I have taken the picture in the long direction, so L minus C1 by 2, you will get this length, okay. So for the calculation of moment, omega L square by 2, omega is 118.3, you have calculated the pressure, L is 1.425, okay, here, or you can put the directly formula here, divided by 2, omega L square by 2 for cantilever slab, 120.11 kilonewton meter, that is for 1 meter strip, okay. So our that is our square footing. So bending moment in short and long direction will be same, 120.11 kilonewton meter. So now two-way shear check is okay. Now I will check for one-way shear. For calculation of one-way shear, we have to calculate at a distance d from the face of the support. So QU into L minus C1 by 2, you will get this length, or you can say L by 2 minus C1 by 2 minus D. You will get the applied shear value for one-way shear at a location distance D. Now calculate the capacity using one-way shear formula, 0.75, 0.17 under FC prime BD. So unit strip B is 1000 millimeter, D is 390. So the value is 224. So that is again greater than our applied shear. Now one-way shear and two-way shear are okay, means our depth of footing is okay. If any checks one-way or two-way shear fails, you have to increase the depth of the footing. So now we have calculated the moment, okay, the moment value is 120.11 kilonewton meter. So you can use the formula either using table or either using the exact formula, that is 0.85 FC prime 20 300 multiply by 1 minus under root 1 minus 2.614 multiply with moment. Our moment is 120.11 x per 6 power 6 divided by FC prime 20 multiply with BD square. Our B is 1000, D is 390. So square, here bracket will be closed, enter. So our reinforcement value is 3.00 to 10 raised power minus 3. So answer will be same, 0.003 row value you will get. Okay, steel ratio value here. So you will multiply with BD 1000 to 390, you will get the area of steel 1170 millimeter square per meter. So AS minimum, that is for 300 grade steel, that is 0.002 BH, so that is 900 millimeter square. The formula is BH. So our provided steel is greater than the minimum, so that is okay. So now we will select the spacing. Okay, you can again select for the number 3 bar, area of bar divided by spacing. Okay, area of bar, that is number 13, that is 129, area of bar divided by total area, that is 1170 multiply with 1000, you will get the spacing. Their spacing is 110 millimeter center to center, or when you will use the bar number 16, you can provide the larger spacing 170 millimeter. So I will recommend use number 13. So you can both, you can, it is up to the designer. So now our steel is also calculated. Now we have to check that the spread that we have discussed, when the load transfer from the column to the slab, it make a projection, one they show vertical, two horizontal. So for that check, or either we needed the double bars or not. So here, so A1 is the area of concrete that is of our column, that is 450 millimeter by 4. A1 is the area of concrete, so that is 450 by 450. Okay, that is 202 500 millimeter square. So A2 is the area of an enclosed figure consisting of column size plus an additional dimension of minimum actual projection beyond column and 4 times total depth of slab on all 4 sides. What is saying? I will calculate with the formulas. The less projection out of 4 sides must be used on all 4 sides. What is saying? So there are two options. We can calculate A2 just by multiplying 4 times with A1, means on all 4 sides. Okay, so A1 is 202, multiply with 4, you will get 8100 millimeter square. That is calculated based upon you can say formula. Okay, so take the under root, answer you will get 900 by 900. Okay, so now I will use the formula for the calculation of actual projection that will form or the loading path that will go at the end of the footing. Okay, here is the footing. Here is a spread of the load from column to the footing slab. So that with this law, 1 vertical, 2 horizontal. Okay, so what will be this? Okay, dimension. So that will be C1 plus 4H. H is the depth of the footing. So I will again take the calculator. So you can see C1, that is 450 plus 4 times 450. Okay, so our the projection needed as per our calculations, that is 2250 millimeter. So this dimension must be. So but we have provided the projection actually. So our total depth, total projection that we have provided in the footing, that is 3 meter by 3.3 meter. So I will subtract just 330 minus 450. So this much footing length is provided to accommodate the load from the column to the slab. So our actual projection is 2850 millimeter. So that is okay. So now when we divide the A2 is greater than 4A1, so our actual is greater than this one, so that is okay. So our provided actual projection is greater than as per needed in the calculation C1 plus 4H, so it is okay. So now we will use the formula under root A2 divided by A1 equal to 2. So in the slides this is the same formula. In the slides that is the formula 5PN. Okay, so that is PU, not BN. So that is a little mistake in the book. So formula is 5 into 2, that is under root A2 divided by A1. Take the under root, the value is greater than 2, so we will take 2. So 0.85 FC prime into A1 divided by 1000. So our value is 4475 kilonewton, that is greater than PU, that is PU. Applied factored axial load. So foundation concrete, so this is the foundation concrete, this is the foundation concrete capacity is greater than the applied load. So our foundation concrete is capable of resisting the column load even without the dowels, means there is no need of dowel. So let's take again the calculations. We have checked there is no need, but still we want to check. So that is the formula applied, that is PU minus phi 0.5 fc prime ag divided by 5 fy. So when you will calculate, you will get the answer 0 or in negative. So it means there is no need of double bars. So but if there is no need of double bars, but you will still provide the doubles as per ACI requirement, that is 0.005 AC, that is for AG area of concrete of column for 50 square, so 1013 millimeter square. So for number 19 bars are sufficient as double reinforcement. However, 8 number 19 bars may also be used for a conservative design, because already in the column 8 number 25 bars are present. So you have to make overlap a good connection. You will provide 8 number 19, not 4 number 19. So now the development length for each bars. So in our design, so number 16 bar that will be used here, that we have calculated number 16 bar. How much development is needed for number 16 bar? So here is the development length formula, 0.485 fy over fc prime die of bar. You will put the die of bar, you will get the development length for 21 millimeter when the development in tension. Here when the load come on your footing, then on the bottom side there will be tension and on the top side there will be compression. So steel will be provided at the bottom side. So number 16 is present at the bottom. So the development length is calculated for the bottom bars for number 16 bar, that is 521 millimeter. Now development length in the compression for number 25 bar, that is present in the column. So here LDC in compression 0.24 fy over fc prime under root die of bar should be greater or equal to 200. Our value is 564. So for double bars development length in compression, our column will be in compression. So the value is 429 millimeter. But required number of parts for double minimum, that are 4, but we have provided 8. So we can reduce the development length by how? Required area of doubles, provided area of double 1013, provided 2272. So multiply with 429, that is for number 19. So you need to provide the development length 192 millimeter. So here again the compression splice, where this 2 bars will be spliced. Okay, compression splice length for number 19, that formula is 0.071 fy is the grade of concrete, grade of steel, f into db greater or equal to 300 millimeter. So that is the development length formula in different parameters. Here you will get the value 737 millimeter. So you can approximate to 0.75 okay meter. So here is 0.575 meter. So that is the sectional view, that is the top view of the footing, means number 16 into 170 millimeter in the long direction and the short direction, 3.3 meter by 3.3 millimeter, 3.3 meter, 100 millimeter concrete bed, and 50 millimeter will be the footing thickness. Okay, so how this formula is f and parameter and LDC, that all is discussed in the chapter 11 of development length. All formulas are also present. Okay, so here f parameters. Okay, what is f? F will be 1 if fc prime is greater than or if less than or equal to 4/3, means 1.33. So all values of development length is given in chapter 11. So that's all for today's lecture. Have a nice day.